So last time we learned that there was a subject called mirror symmetry, and we learned what it was about the following thing. You have some x, omega, and symplectic manifold. And you were supposed to believe, it's some kind of article of faith, that this has to do with some y, j complex manifold. And there's a long story about what have to do with means, but the aspect of it which somehow we discuss in these lectures, homological, is that the homological mirror symmetry, which concerns the supposed relation between this Fukaya category, which we mentioned last time, and what's called category of coherent sheaves. This, so this is what homological mirror symmetry is about. And maybe it's worth pausing to explain what is easy and what is hard in this subject. And typically, what's easy is understanding this. So this is usually easy. Right? So in improving this kind of equality, the main work tends to go into computing this side. So that's not easy. And why is it not easy? Well, at least one reason is that computing this guy involves this counting of holomorphic disks, which means solving some, it's a non-local problem. Holomorphic disk kind of, goes all over the place. You don't know where it is. And actually finding them requires you to solve some PDE. So, so in particular, and you must count holomorphic disks. And which in general is hard. Okay, so that's now. So our life would be made a lot easier if we could do something other than counting these disks. And the point of the talk today is to explain to you what is this other thing that we can do. And the setting in which we can do this other thing is, so we have this, so we ask now that this be exact symplectic, like it was discussed yesterday, and in fact, maybe Weinstein. So you have to remember what this means from the talk before, although it won't actually be relevant here. And in this situation, we had this rat Fukaya category yesterday, and the fact, which I will not be explaining to you, but the fact which explains why we discuss what I'm going to discuss here is that there's another equality of this guy with something called microsheaves, and on the skeleton of X. So remember last time you learned what is this skeleton of X? It was the conical, some kind of Lagrangian subset inside X, which carries some aspect of the geometry of X. And this this equality, it's maybe not easy, but it's true. Okay, so this is known. And so what and what kind of thing is this? This guy, it has the virtue that it's somehow topological in nature, so it's topological. And in particular, there's no of this holomorphic disk. So local, no disks. Nothing on the board is meant to be, I haven't gotten any mathematics yet. This is just the situation. Now let me say a few words about why it's remotely plausible that, why is it remotely plausible that something, this kind of thing which involved disk over here, should ever be related to something without any disk. And the model situation, so I have to remind you how Morse theory works. Morse theory. Okay, so Morse theory, if you have some manifold X, let's call it M. So manifold M, and you have some function f from M to R, then you can build the Morse complex, and that's a chain complex. You have the C star Morse. And this is a chain complex that is generated by critical points of f. There's one generator for each critical point of f, and it has a differential which counts these gradient flow lines. And this thing in this, we were discussing this Lagrangian flirt theory yesterday, and this thing actually is more or less example of this kind of Lagrangian kind of complex. You have M. This whole picture is happening in T star M. You have the graph of df. That's some exact Lagrangian in the cotangent bundle. df is 0 at a critical point of f. So these are the critical points, f. And so, this thing, it's like the Floer complex, this Hom between these two Lagrangians generated by these things. And then I reminded you this in this Morse theory, this kind of flow lines or whatever, what you count, and in the Lagrangian flirt theory, instead you count these disks. So as you see, they're not very different from these flow lines. That's a reminder about this Morse theory. Now, what does it have to do with the discussion we have now? What makes it possible to have a disk here? Well, if you think about Stokes' theorem, what makes it possible to have a disk here is that as you travel along here, the integral, so that the integral of lambda along this line, okay, because lambda along this line is 0. So that's what Stokes' theorem tells you. So what's making it possible to have this disk is that, okay, this guy, it's somehow separated from the 0 section. So you should imagine that if you now rescale f, okay, imagine rescaling f. Well, what happens if you were to do this is this guy, it goes down to the 0 section. And if it's going to go all the way down there, now it's not possible to have this disk anymore by Stokes' theorem. Because its area would have to be 0. There's no holomorphic curve with area 0. But on the other hand, every point is critical. Okay, so you can also no longer do Morse theory. So in this limit, what you're supposed to think is that this Morse complex, Morse, becomes something. And well, what does it become? It depends on your point of view, but one point of view on it is it becomes a de Rham complex. Okay. And so what is the nature of this de Rham complex? Well, somehow this D, its virtue is that it's entirely local, but it's somehow you pay the price that something is happening everywhere on M. You can't concentrate locally on this thing. Now, what does it have to do with this skeleton business? Well, if you have this kind of Weinstein manifold, and you have some skeleton, so this is X Weinstein, and you have some Lagrangians, and here another Lagrangian. Now, and you have this Liouville flow, okay? And as you use this Liouville flow, you could use it to push everything down to the skeleton. And if you were to do that, that same Stokes' theorem argument tells you that in the limit, none of these holomorphic disks can exist. They all have to go to area 0 just by the Stokes' theorem argument. So that tells you that if if you are going to, it gives you reason to believe, together with this kind of thing, that maybe there's some theory living locally on the skeleton which recovers this entire Fukaya category. Okay, so this is some kind of cartoon about why you should believe this. I mean, why you should believe that anything like this is possible. I haven't yet told you what this thing is, but that's why you should believe there's some kind of, it should be some kind of local theory. Going from that cartoon to a theorem, actually, I don't know how to, take that reasoning and actually turn it into mathematics. Nevertheless, you can prove this theorem. It takes 400 pages. So I won't be explaining that. But what I will try and explain is how I do an example introduce you to this, this item. Maybe it's good to have one explicit example of this thing, okay? So we had example yesterday of a pair of pants. We have this pants and you draw a skeleton, which I'm going to draw like this. Okay, so that was the skeleton of the pair of pants from yesterday. There might be a bit of a difference between how, did you draw this yesterday? Might be a bit of a difference between how he drew yesterday and how I drew today, but this I've just chosen a little bit differently of a vector field. Anyway, it's a vector field. So one thing that I want you to pay attention to about this skeleton is that locally, this in this example, this is not always true, but in this example, locally embeds as a conic Lagrangian in a cotangent bundle. Why? Well, which cotangent bundle? I can take T star S1. You have to identify the ends. Here's the here's the S1. That's this S1 that you see here. And then there's the piece coming out, probably like this. And then you have to connect up this piece. So it's obvious that this is locally conic in the cotangent bundle. What is conic? It means that the cotangent bundle rescaling preserves it. Or in other words, Liouville vector field preserves it. But what about this other piece? Well, this other piece, it also looks like zero section of cotangent bundle of a different kind of copy of the interim. Okay, and this kind of picture, one dimension higher, is something which will show up in Doan's talk Friday, Thursday, Friday. You're giving a talk about this four-dimensional construction.
His paper. Yeah. Thursday.
Thursday. So you'll see a higher dimensional version of this on Thursday. So if you don't understand that, and now somehow, today is the time to. Okay, so
and do you understand that? You can. It's something you can understand. So if you don't, try.
Yeah, that's right. Okay, so this picture. And what I will start with today, and probably I won't get any further than this, is telling you how to compute about this microsheaves in this special case, when the skeleton locally embeds in the cotangent bundle. And that sounds like a pretty special case, but all the same, it's going to be enough for every application to mirror symmetry that I know.
sorry. Could this thing be uploaded?
I don't know. This is good exercise. Well, maybe we can maybe we can find out. Let's see. I can look at the boundary of it. There's like this this hole, and then there's this. You should count somehow how many holes that there are. So how many holes are there? And maybe it should be the other way. Okay. And actually, whether it's the other way or not, also maybe this one should it should.
So
I'll do it right. Okay, so one possibility like this, and that's one possibility that he's saying. Another possibility is that I drew this wrong.
Yeah.
And it's like this. And actually, both of these are probably okay. This is a good thing to work out in discussion time. Okay, so that's where we'll go today.
Maybe can you put a question mark so that people? Yes, perfect. Let me know the next question.
Yeah.
You have to work this out. Okay, which one?
I think actually both of these will be okay, but the original one I drew probably not. Okay. So now I have to tell you about sheaves. Is there an eraser?
There is.
Oh, okay, thank you. So sheaves kind of he has a reputation of being a bit technical subject. It has some technical aspects, but somehow. I will tell you where I hide the technical aspects. So these days it's gotten easier to hide them. Okay, so it's. This seems like a bad idea. Okay. So when you learn about sheaf, you first have where does a sheaf live? It's something which lives on a topological space. Okay. If you don't know what a topological space is, it can be manifold. And first, I have to tell you what is a pre-sheaf. Okay, so I'll say it the precise way first, then I'll tell you what it means. So the precise way to say it is it's a functor from, I take the category of open sets in T, I take the opposite category, and I take a functor to some other category. And but what does that mean? It means that if I have an open set U in T, and I have an open set V in T, and maybe U is contained in V, then I get elements, so these live in T, and I get elements of C called F of U, F of V, and this op means that there's a map, and it goes this way. Okay, so that's what it means to be pre-sheaf. And this word functor, it means this is compatible with, like including open sets and other open sets and so on. So that's pre-sheaf, and maybe I should give some example. Okay, so we give several examples. So one, I'll just tell you the value on an open set, and you have to think yourself, how does the restriction work? So F of U, here's, I take all functions from U to R. I could take continuous functions. I could take compactly supported functions. I mean, I could try to take this. I realize now that I'm writing this, it is not an example. Why is it not an example? Well, if I have an open set, I could have something compactly supported in this open set. It could be maybe supported in this compact in there. But then I restrict to the smaller open set. And now in this open set, maybe it's 1 on here, but now it's not compactly supported anymore. Okay. So because now it somehow takes up the whole thing. So this is not an example. Okay, let's continue. I could take constant functions. I'll give you more interesting examples later on, but I want to give some first trivial examples. Constant functions. And not many constant functions, just somehow R of them. I could take locally constant functions. What's the difference between locally constant functions and constant functions? Well, if U is disconnected, then there's R many constant functions, but locally constant functions can be different on each component. And now I have to, and now I make a little bit sophisticated example. I could take some model for chains on U. Okay. So for example, if you don't know any other cohomology theory, maybe I should put chains valued in R, and then it could be drawn cohomology. So that's what's a free sheaf. Here's some example. These examples, and you should think of sheaf as somehow generalization of like kinds of functions. So other kinds of sheaves are like functions not maybe valued in R, but somehow valued in somewhere else, or valued in different things locally everywhere, and so on. I'll show you some examples. So that's free sheaf. And then there's you can ask how do you make new sheaves, free sheaves from old ones? The most basic way is what's called push forward. So you can have some map x to y, should be a continuous map. Then given a sheaf, given sheaf on x, I can make the push forward f the sheaf on y. Well, it's given by the following formula. So this thing, it should be a sheaf on y, so I can apply it to an open set of y. And I should give you some value of this sheaf. Well, I had a sheaf on x, so I can apply f to an open set in x. This little f map is continuous, so this is an open set in x. It's the only thing you could possibly write. And this how you make new free sheaves from old ones. It's called push forward. And there's one other important concept that we will need. It's called stock. Now, I apologize if you already know all about sheaves, but Umu told me I have some even undergraduates here, so I somehow introduced from the beginning. And stock, what is it? Well, I just write the definition. If I have a sheaf F, it's something which is defined at a point as it's what's called a limit. So limit is something, maybe you use the limits from analysis. There's not that kind of limit. It's some kind of categorical notion. I'll explain what it is in a second, maybe. It's the limit over neighborhoods of P of the value of that sheaf on that neighborhood. So maybe rather than say precisely what limit means, I'll just tell you at least what's an element of this thing. Okay, an element of this limit, it's a value. It's somehow elements of f of u for somehow the sufficiently far along u's near P, such that it's compatible with a restriction. Okay, so what does something like this here look like? If you have P and P is contained in U1, which is in U2, and so on, and then maybe it also goes the other way. Okay, so we have U0 and then U-1, and so on, and all of these P lives in all of them. Then an element of that limit is something like you have C2 in f of U2, which under the restriction map to f of U1, this C2 gets sent to some C1 and so on forever. Okay, that's the kind of thing which this limit is. Example is if I take, maybe if I had a smooth manifold and I took somehow like convergent power series as my functions, then the stalk is going to be something like power series. Okay, so that's this notion of stalk. I'll give some examples of this in a second. But I promised to tell you about sheaf, and so far I've only told you about pre-sheaf, so I have to tell you what is a sheaf. The basic idea is that sheaf is something which is determined locally. And the formal definition is it's something which sends covers to limits. So sheaf, it's covers to limits. And the formula is that if I have an open cover, I'm going to take a union of some open sets, UI, indexed by some index set. Okay, this is some open set. And the statement is that this is computed by, so I'm going to write some formula. It's not so important what this formula is. What's important is that there is a formula. So it's a limit of overall somehow sub-collections of this I of f applied to the intersection. Okay. And let me just go over, so this is what it means to be a sheaf. Property of limit means there's always a map in one direction, and because there's always a map in this direction. And being a sheaf means that map's isomorphs. Now, let me just go over here and say which ones are sheaves, which ones not. So this one is, this one is, this one is not. Why not? Because if you have a disjoint union of something and you cover it by that disjoint union, well, this formula tells you you're allowed to specify separately on the different pieces what you want the value to be, which is okay for locally constant functions, but not for constant functions. Okay. And now this one's a bit delicate. So here I said valued in some category. I didn't tell you what category is, and I'm definitely not going to tell you what is infinity category. But if I were, the correct place for this to take values is in the infinity category of chain complexes localized along quasi-isomorphisms. And the reason I write this kind of funny way, so if you've ever seen the definition of sheaf, it probably didn't look like this. But the reason I write it this way is when you say it this way, then this notion of limit, for the appropriate notion of limit for infinity category, this one also sheaf. Okay, so that's about sheaf. It's not so important that you understood what I set up till this point. Now I do some examples, and that may be more important. Actually, while I have this up here, maybe I'll do an example of this push forward. So if I have an open subset, V included in X, and let's say I have an inclusion, then I'm going to write ZV with the locally constant sheaf on V, whose stalks are all Z. So this one I wrote before I would call RV, and this one maybe ZV. And I could consider its push forward. Okay, so this is a sheaf on X, and it has the property that if I do this and I take its stalk at some point, well, this is 0 if P is not in V, and Z if P is in V. So if you didn't understand anything about sheaves until this point, well, you can just pretend that they're characterized by this property. That's not literally true. It's like this sheaf, it's characterized by this property plus some kind of continuity.
Can I suggest one more example of sheaf, because maybe people know it, like vector bundles. If you have a vector bundle, sections of a vector bundle over open subsets of the base is another example of a sheaf.
Okay, let's put that over here. We can have 3.5. If I have E over B, and I have a sheaf called F, which F of U is sections of E over U. And the other examples are special cases of this example when the vector bundle is the triple vector. But actually,
holomorphic vector bundle, you can take holomorphic section and so on. It's very kind of robust definition. Generalizes everything.
So now I have to explain to you. So I explained now what is pre-sheaf and sheaf and some example. Now I have to explain. This you would learn in any course on sheaves. But now I explain to you sheaf theory. So sheaf theory, it takes place on the space T, or on the manifold M. The microlocal sheaf theory is about how a cotangent bundle of M plays some role. Okay, you might ask, how is the cotangent, what does cotangent bundle have to do with anything? Sheaves live on M. And the answer begins with the following definition. So I need M fold, F, a sheaf on M, little f from M. Okay, let's not use this little f. Phi from M to R, a smooth function. Okay, there's this data. And now I'm going to define something which is a bit similar to stalk. It doesn't really have a name, but I'm going to call it microstalk. And first I'll tell you the formal definition, and then I'll tell you how to think about it. So it's something which you associate to this sheaf, this function phi, and a point in M. P is just a point in M. And its definition is the limit, again. So this teaches you eventually you have to learn what this limit means. Over open sets containing P, it's like the stalk. And now I write something called cone. We'll discuss in a second what cone is about. But inside here, I put the value of the sheaf on that open set. That's one thing I'm allowed to do. And I also look at the value of the sheaf on the inverse image of the negative half lines intersect this open set. Okay. Maybe it'd be helpful to draw a picture. And so let's ignore this limit for the moment. I have some open set U. Maybe my function phi is just the projection to the real line, looks like this. then I have the free image of the this half line. I guess I should ask this. I'm going to ask P if P is 0. I ask for the so U is the free line, and then this part is the free image of the negative half line. And I can look at f of u. That's something I'm allowed to do to a sheaf. And the sheaf, the one thing you're allowed to do to a sheaf is you have the restriction map to open subsets. And the inverse image of the lower half line is some open subset, so I can study this map. So okay, so let's just draw pictures. So I have the whole open set, and I have the somehow bottom part. Okay, I have this map. And if you have a map between objects, some category, you don't even know what it is, there's one question you can ask. Is it an isomorphism or not? Okay. Now I'm going to be working in some category like chain complexes where there's something called cone, which has the property that it's 0 if this is an isomorphism and not 0 if it's not an isomorphism. Okay, so the job of this guy is to detect whether or not this kind of restriction is an isomorphism. That's the job of this person. What time is it? What?
20 minutes.
Okay. This is my first talk. Now I compute for you some examples of this thing. Oh, maybe first I'll tell you about how to think about it. So you should think that everything I say in this box, this is going to be all lies, okay? But how you should think. Well, if I didn't have this second piece and you ignore this word cone, that's just the stalk. Cone of the stalk 2. And like, what is this thing? Well, it's kind of like the stalk at some infinitesimally close point, but slightly down. It's like the cone between f by some map that has to comes from a sheaf to p minus epsilon d phi. Okay, that's how you should think about this. Maybe. And I'm going to use this lie to compute. I mean, like any sheaf-like function. more or less. Picture?
Yes.
Okay, can you hear me again? Yes, oh, yes, okay, very good. So, yeah, so I'm going to consider two functions on R. There's X, which is the identity from R to R, identity, and minus X, which goes minus the identity. Okay. Maybe I'll just call them identity and minus identity. And then I'm going to write whether I'm going to try and indicate when this cone is 0 and when it is not. Okay. And I'm going to do it using this kind of this lie and also this this statement. So how about this one? Well, here I should, with the identity, I should compare the stock at 0, which according to that proposal is just 0, because 0 is not included in here, with the stock at a small negative number, which okay, here I put positive, so the stock at a small negative number also 0. So I'm comparing 0 to 0, and they're equal, so the cone 0. Okay. But how about this one? Now I should compare the stock at 0 to 0 to the stock at a small positive number, which is not 0. This is non-zero. And okay, how about this one? Well, I compare stock at 0, which is non-zero now, to the stock at a small negative number, also non-zero. And moreover, they're both z. Okay, so I'm comparing them. You have to compute what the comparison map is, but maybe it's identity, and so it's still 0. And if you compute, it's still non-zero. Now I'm going to just fill in the rest of the table, and then I leave it as an exercise for you to check it for yourself. This 0, 0. This one. Okay, 0, 0, non-zero, non-zero, and this is non-zero. So the first exercise in the subject is check this table. I still haven't gotten to the point where I explain something about cotangent bundle, so I do it now. With this definition of microsupport. Definition. I've written this definition. Here we are. The microsupport of a sheaf F. So this is for F is a sheaf on M. The microsupport of a sheaf on F. Well, okay, what's it going to be? It's going to be some kind of subset of the cotangent bundle. And what it is it's the locus of points P, C. P is a point in M, C is a covector, where there exists some phi such that d phi at P is Xi. Phi of P is 0. And the microstock at phi, this phi P, is not 0. Okay, it's this kind of thing. And you take the closure. Yeah, that's the definition. Let me draw for you. So basically, it's the codirections where you have, it's like it's the possible B phis where you have a non-vanishing microstock. So I'll draw for you now the micro supports in all these examples. Okay, I didn't tell you about micro support in the 0 section. It's just the same as where the sheaf is non-zero. So in the negative codirection, you get something. So in this square is a picture of T star R. The pictures look like this. This one, this one, this one. This one, this one, and this one. Okay. So that's that's part 2 of this first exercise in the subject. Compute that. And now we start to have a sense of what this has to do with symplectic geometry. This is some kind of, there's some kind of Lagrangians. Maybe you should smooth them out a little bit. Okay, so that's that first example of micro support. And now how we use this thing. So far, I was discussing you have a sheaf, you do something, you learn directions in the cotangent bundle along which the sheaf is changing. But now I want to reverse the reasoning and pick, to begin with, some subset of the cotangent bundle. And study sheaves whose microsupport is contained in there. So for lambda and T star M, we write sheaves lambda M for sheaves on M, F in sheaves M, such that the microsupport of F is contained in lambda. In other words, I tell you at the outset in which directions I allow the sheaf to change. And let's do an example. So example, I take M to be a real line. And I should draw for you now some lambda. So, and lambda equals, I don't know why I decided to draw it in orange, but I'll draw it in orange. Here's a picture. This is a picture of the 0 section plus the positive conormal at 0 in T star R. Okay. Yeah. So and let's study sheaves on this lambda R. Okay. Well, I've already given you 3 elements in there. It looks like this one's in there, this one's in there, and this one's in there. Okay, but now I'm going to forget that I did that already. Let's compute this from somehow first principle. So, okay, so I have again this picture, and I cheat a little bit. So okay, so let's it's a sheaf, so it assigns values to open set, and let's pick out some open sets and contemplate them. Here's some kind of open set. This one, maybe this one, and this one. And okay, sheaf assigns some value to these, and let's call it A, B, and C. Okay. Now, maybe something not so hard to understand is that if I change A a little bit, I make it like this or like this, then the value of the sheaf on A is not going to change. Why? Because somehow there's no micro support happening out here. So the sheaf can't change as I move things around in this outside area. Okay. There's a formal statement to that effect. And so these three open sets I've drawn are really the only kinds of connected open sets which you should consider. And then, well, there's this A, it kind of contains B and C. So F of A is going to map to these ones. And remember that now what was that condition? Like this thing is basically the stock at a slightly negative point. And this one's the stock at a slightly positive point, more or less. And this one is stock at 0. And so this micro support condition, well, it's telling us that the stock at 0 is supposed to be the same as the slightly positive stocks. In other words, it tells us this had better be isomorphism. Okay, so let me write that in a little bit different way. We get to assign 3 elements of our category, maybe vector space, maybe chain complex, whatever. There's maps between them. And the map in this direction better be isomorphous. And since that one had better be isomorphism, we may as well just erase it. So this calculation tells you that this sheaves, it's the same as representations of this quiver. In case you don't know what that is, just means that I put a vector space, I put another vector space, and I put a map. And let me do a similar but a bit more complicated example. So, okay, well, we had pretty good fortune there. Now we can just go crazy. Okay, just somehow in the same dimension, just put as many of these as you want, like this. Now what? Well, the same kind of reasoning as before says that, well, you should probably specify values here, all these kinds of points. Okay, but there's too many, but okay. But values all these points, and then there's going to be arrows, so on, and some of these arrows are going to be isomorphisms. And which ones? Well, we saw that when the spoke points up, this kind of arrow this way is an isomorphism. I leave it to you to check that when the spoke points down, the arrow in this way is an isomorphism. So isomorphism, and so on. And so you collapse it a little bit. Okay, this one was out of control. I'll do a smaller one. So here we have this one's an isomorphism. These ones maybe not isomorphisms. So all told, you have this kind of quiver. Okay. Okay. So sheaves on this thing is those representations of this quiver. Maybe I do one more example. Let's glue these ends together. I guess this wasn't really consistent with my notation, but never mind. So let's glue these ends together. So we have this kind of one spoke pointing up, one spoke pointing down, and then on the circle. A different example. Well, you can kind of see it's going to be like this one, but I had better glue these 2 points together. So it's representations of this quiver. Equals, and a bit simpler name for that is okay. Now, if you study algebraic geometry, you recognize this immediately as category of coherent sheaves on P1. And so I have just, I will talk more about, but let me just tell you what mirror statement this corresponds to.
What is the each for sheet? Because no, yeah, this one. I just engage with it.
It's like this, but I've glued this end to this end. It's just on circle. Okay, so that's in case you don't know that last fact about coherent sheaves on P1 being representations of that quiver, let me explain to you just in 3 seconds why it's true. The point is that at P1 and co-P1 inside here, the structure sheet of O1 and how to say it, HOM O1. It's C. And these two generate anyone else can make out of these guys. And so you have these two guys. The fact that the endomorphisms are C means you just put dots there, and then HOM O1 is C2, which means you put 2 arrows here, and HOM O1. So this kind of fact is why it's representation set purpose. That has nothing to do with what I'm discussing today, but just in case you didn't know what I explained. But then, so putting all together, what is this mirror symmetry statement? It's that, so I had this thing, but now let's remember that we do symplectic geometry. Okay, so this was the skeleton of someone, so this is glued up to itself. And I'm going to now thicken it up a little bit. So what does this look like? Somehow it's this. So you have to remember these are glued together. It's kind of this Liouville sector. Okay, and now I invoke that theorem which I mentioned at the beginning. I learned that this thing is coherent sheaves. And how much time do I have?
-5.
Can I take another -5 minutes?
But
is it okay?
You can go maybe like 2 minutes.
Okay, I'll go for 3 more minutes. I'll leave this because this is good exercise. I want to explain some kind of taste about going going beyond cotangent bundle. Okay, so as something we're going to do, I think in this week, we consider these chains of P1s. So this is about one P1. But what about this kind of chain of P1? So P1, P1, and so on. Okay, then this guy. I said that he was supposed to be somehow a circle with two spokes pointing out. I'm going to do something kind of forbidden and write it on this side. You have to imagine that it actually comes out the other side. And then this other guy, he also has like this, and then this one also like this. Okay, I made 6 of them. Now, if you contemplated further about this microsheath, you would learn, maybe I explain this next time, that somehow, P1 has points 0 and infinity. And you learn that the restriction map from co P1 to co of 0, or co, these are just points, okay, this is infinity, and this is just the vector spaces, is the same as taking microstocks here and here. And this sheaf property I alluded to at the beginning, what it tells you is that the gluing of these P1s together at this thing, it matches if you glue like this. Okay, and if I were to, if I had drawn this properly, and if I were to now thicken up, like draw, surface would be torus with 6 punctures. Maybe I'll stop there. We can discuss this more maybe next time. In this way, you can bootstrap from this kind of knowledge of this like kind of local calculation, which I didn't do it maybe quite as slowly as I might have preferred, but I promise you, you can understand everything about this calculation. But you can bootstrap from that up to this kind of smoothing of this. I mean, the mirror or something like this. And maybe I stop there.
Okay. Thank you. Okay, any question for Vivek from the participant?
Is there Microsoft support all these languages?
No. If for the sheaves we're interested in here, yes. But okay, maybe I'll tell you the following. So first, let me tell you the answer no. So example, if I take if I take functions, so f of u equals functions of u to r, then the micro support of this f is just everything. Because like if I shrink the open set at all, I change what functions that there are there. But so that's the no part of the answer. There's a yes part of the answer, which is the following result. I should have mentioned all this microsheaf theory. If you want to learn it properly, you have to read a book by Kashiwara and Shapira called Sheaves on Manifolds. Okay, there you find all this kind of stuff. But the answer yes. There's a theorem of Kashiwara and Shapira which says the following, that f is constructible with respect to a subanalytic, never mind this word subanalytic, I did write it to be correct, stratification, if and only if the microsupport of f is constructible means that, there exists some way of cutting up your space into locally closed pieces, so restriction to each piece constant. If and only if microsupport of f is subanalytic Lagrangian. So constructibility and microsupport Lagrangian more or less the same.
What happens to this paper representation picture and SI dimension?
So in general, you're no longer so fortunate. Well, maybe what I'll do on Friday. So on Friday, I'll have the following theorem. Yeah, I'll put any toric variety here, and I will tell you what to put here. So that's some kind of answer to your question. Maybe I'll explain that, and if I have yet more time, I'll explain how to glue those toric varieties together to get the kind of soccer ball.
Maybe I have one question, clarification. When you say microcontroller chips and category match each other, and then microcontroller chip category is associated with skeleton or infinitesimal neighborhood of skeleton, or something else, and skeleton plus somehow.
Yeah, should be. I mean, I didn't make any statement like that, but the statement is that you can associate microsheaf category to any germ of contact manifold. So you should take infinitesimal neighborhood of skeleton.